Today's National Soil Survey Center webinar. My name is Sean McVeigh, National Training Coordinator for the Soil Science Division and host for today's webinar, Soil Spectral Inference, a new way of gathering soil information. This webinar is being recorded and all participants join the webinar in listen-only mode. You receive the webinar audio through your device's speakers. There is no telephone dial-in. If you are having audio difficulties, please check the various ways your computer speakers may be muted or have their volume set low, including the speaker adjustments available in the Adobe Connect interface. Be sure to turn up the volume if you need to. You can maximize your webinar experience in Adobe Connect by shutting down Cisco AnyConnect and any other programs that might compete for bandwidth. This includes email and Microsoft Outlook and instant messaging and Skype. Taking a look at our webinar room layout, Adobe Connect has content pods that include feature presentation, chat, and Q&A. Use the 4-hour icon in the featured presentation pod to enter and exit the full screen mode as you choose. To submit a comment or question for me or our presenter, use the Q&A pod and type in your question. We're here to answer your questions. We'll handle technical difficulties the best we can while hosting the webinar and interact with our presenter to answer your questions during verbal Q&A periods. I want to thank Rich Ferguson for being here to support our webinar and introduce our presenter. Rich, I'm going to turn the webinar over to you so you can introduce the topic and our speaker.
Thank you, Sean. It's my pleasure today to welcome Dr. Budiman Minasmi, Professor in Soil Landscape Modeling at the University of Sydney in Australia. Budiman has an undergraduate degree from Universitas Sumatera Utara in Indonesia and a PhD in soil science from the University of Sydney. Budiman is concerned with the role of soil in managing climate change, food, water, energy security, and maintaining biodiversity. Budiman has more than 150 international journal publications, won numerous awards, and is a recognized leader in digital soil mapping and modeling. Please help me welcome Budiman as he gives this webinar about his work in soil spectrometry.
Okay. Thank you, Rich, and thank you, Sean. Thanks, Rich, for the invitation. So we had this conversation about a couple of years ago that presenting a webinar for the NRCS, so we finally make it. So it's good morning here in Sydney, so it's 7:30 a.m. and it's raining in Sydney, so it's good to see you virtually here. So I'll talk a bit about our work or some of our work in soil spectral inference. It's a more general webinar, so it's a presentation just showing our work and some recommendations of how we do things. Okay. So we shall begin. Okay, just a brief introduction. So this is, it's not about proximal soil sensing, but it's related to proximal soil sensing. So it's about a long time ago in a planet far away. So the quiz is for you to start with, which is the first unmanned rover that landed on the moon and equipped with a proximal soil sensor. A, is it on Apollo 11 in 1969? Or it's on Lunokhod 1 in 1970, or it's on Apollo 15 in 1971. So the answer is, it's a Lunokhod 1 in which landed on the moon in 1970, and this is the rover, the moon rover, the unmanned moon rover, and on the bottom of it, if you look at it, it says RIFMA. So RIFMA is a XRF or X-ray fluorescent machine, so it has equipment of an X-ray fluorescent instrument, which was sent there to scan or to sense the moon's mineral content or the element content. So it's not about NIR or infrared, but this is just showing that from early on people have tried to make sensors or a quick way of analyzing soil in situ in the field in the condition where maybe it's difficult to access, or if we want to get the results quickly. So, but they started on the moon, so now we are back on the Earth. So to start with, I'll give you some historical perspectives about the use of infrared spectroscopy in soil science and how we come about to this. And then we'll discuss about some methods that we use in predicting soil properties from infrared spectroscopy. So to start with, as we know, infrared spectroscopy has been, people has been interested in the reflectance of the infrared wavelength infrareds in the soil. So this is the early work in 1965 in the near-infrared regions that Bowers and Hanks from Utah. So they want to know what's the effect of moisture content and reflectance, infrared reflectance. The idea is that they can use this instrument for measuring soil water content. And as you can see, there's the water peak there, and he can show that at different water content, there's a difference in the reflectance of the infrared spectrum in the soil, so that maybe they'll try to design an instrument that can measure water content in the field. And interesting, in the same 1965 paper, so they show that the effect of the organic matter. So instead of measuring organic matter, so the check is the control, the soil, and then they oxidize it. They oxidize the organic matter to see what's happening to the organic matter, so that they can relate the effect of organic matter in the soil on the reflectance spectra. So this is in 1965, and this is using infrared, near-infrared spectrum from 400 to 2500, as you can see. And in the other group, the other active group in the 1980s is the groups in Purdue University in the remote sensing group. So they publish a lot of paper, but it's on the infrared reflectance of the soil. But their main idea is that to use, because of the availability or the upcoming at that time of the near-infrared satellite imagery, so that allow them to, or remote sensing, from the remote sensing point of view, that allows them to estimate soil properties. And even they make a soil spectral library. And I was looking the other day, it's actually the spectral library is available online. So it'll be interesting to see the 1980s spectral library. So this is in the near-infrared regions. But people have looked in the mid-infrared regions as well, so which is usually called the FTIR. So the initial work in the 1970s is mainly looking at the organic matter, because the mid-infrared has a direct or the functional groups. The functional groups, so tables like this has been published at a different papers that assign different, because different wavelengths reflect different functional groups, and it's mainly to characterize organic matter, and at that time the interest is in the humic acid and so on. So this is the 1970s, but also in the Aberdeen, the Macaulay Institute, they are interested in the clay minerals for infrared spectroscopy, and this is also using FTIR, or the mid-infrared. So why minerals? Because the mid-infrared has a very special characteristics of the mineral that you can see. So take a look at the one that is labeled A. Don't worry about the other two on the bottom. So this is the pure reflectance, diffuse reflectance of the soil materials. So they tested with a different pure minerals, kaolinite, elite, and montmorillonite. So as you can see that the spectrum, or the absorbance near the 3600 wave number, you can see that this is the characteristics of kaolinite, right? So the kaolinite looks like the Batman's hat. It has a double peak, and with the one small peak in the middle, and the elite has a smooth peak. There's no sharp peak. There's no Batman's hat, but it has a shoulder. And then the spectrite, the montmorillonite, has a much broader shoulder, right? So remember this. This is the 3600, the Batman's peak, and then the shoulder, and then the white shoulder, kaolinite, elite, and montmorillonite. So There are also regions at the 2,000 or 1,000 something, but we won't worry about this. All right, so remember this. And this is used as well up until currently, so this is 2016, because if you want to characterize a mineral rather than the XRD, you can look at the mineral transformation as well. So this is a work by Ryan, and they are looking at the transformation of a smectite to kaolinite and halloysite in a tropical region. So this is a smectite, the broad with the shoulder, and then it transforms into kaolinite, the Batman's pick. And then later it transforms into halloysite, right? So this is in the region around 3,600, but there are also information in this region of 1,000, right? So a quiz for you. So just look at curve A again. Curve A, don't worry about B and C. Curve A again. So what is the dominant clay mineral in this soil? And the answer is, it is natri xeralf. It's an alphy soil with a sodium on it, and in a dry area, xeric area, and the K is for kaolinite, so it contains about 50 to 65% of kaolinite, which you can see directly in this region, the batsman's head, right? And so it is a characteristic. It is the mid-infrared. It has a direct interpretation of the mineral, right? And then the second question is, what is the dominant clay mineral in this soil? So if you remember this, and the answer is, this is a aridisol natra argid, and it is this is kaolinite 20 to 30%, but elite is 40-50%. So the elite is the shape of the elite. And the other thing is that it has an extra peak like this. This is very visible, and this is due to carbonate, right? And the final one, what is the dominant clay mineral in this soil? It's a bit tricky. It looks like elite, but it's in fact dominated by morillonite. So although there's some difficulty, but you can actually see directly that there's a relationship. The shape itself is indicative of the clay minerals, which is very, very basic and very intuitive, and which is different from the near infrared. Near infrared is the spectra is broader and it's more difficult to interpret because it interfered with the other minerals. So in the 1998, this paper is already asking that this. So it's already 20 years ago that can mid-infrared diffuse reflectance analysis replace cell extractions. So this is in the Australian Journal of Experimental Agriculture. Les Yannick and James Kemstats, they are from CSIRO in South Australia. And if you look at it, that they say that recent developments in infrared spectroscopy, the FTIR, the mid-infrared, and computer software with decreasing spectrometer costs have resulted in an increased potential for soil analysis. So the idea the 20 years ago is that now that there's a powerful computer, powerful software, powerful algorithms that allow us to interpret the spectra, and also the price of the spectrometer has decreased. So it all depends on the multivariate data analysis. As you can see, although you can interpret it qualitatively, like what we did before, like that's the shape of the peak, indicative of the minerals, but we can now with the multivariate data analysis, which can take of variables that 1,000 or a few thousand variables, what we call ultraspectral, and then analyze it to predict soil properties. It's because of the development of the multivariate data analysis, in particular principal component analysis, which is already available a long time ago, and then PLS regression, which was developed in the 1960s, but then become popular when there's a chemometrics because of the speed of the computer, and maybe because of the processor, the increased speed of the processor that is available to process the spectra, and personal computer that makes it easier. And then chemometrics in soil was applied in the 1990s, and then machine learning also come about in the 2000 and was made available rapidly, was made available that people can use this kind of tools to analyze the spectral data. So as you can see, the mid-infrared contains lots of information about the minerals, about the organic matter that makes it very attractive for lab analysis. So how do we convert the spectra to the soil properties? So if we look at the basic law that governing infrared or spectroscopy is the Beer-Lambert's law, that's saying that the amount of reflectance or the amount of observance is proportionally related to the concentration. For example, if the Beer-Lambert's law was observed, then we can do a simple univariate calibration at a particular peak or particular region of a wavelength. We can do a simple univariate calibration that the height of the peak is a function of concentration. And indeed, in some instances, this can be observed. So for example, in this paper in 2015, they are looking for gypsum for salts in Iran because they are already sold. There's lots of gypsums. And there are particular regions in this, for example, 1748 nanometers, which are indicators of the gypsum concentration. So relating this height of this peak may be indicative, may be a quantitative indication of the amount of gypsum in the soil. And also in the area where there are contaminants or amount of materials that are not usually present in soil, we can directly observe that this addition is due to the foreign material or contaminant. This is an example. This is the spectrum of a diesel, the one on the bottom. This is the spectrum of a diesel. And if you look at that, there's a particular peak here, around the 2900, which is due to the aliphatic component of the organic hydrocarbon that is particularly present in diesel, and also this region is due to the aromatic. But if you look at it, and this is this region, and if you look at it, this is a loam and with quite a high amount of carbon content, 9% of carbon content. If we add the different amount of diesel, you can see that this peak around 2900 starts to appear. So this region itself is indicative if there is a high amount of diesel amount, or sorry, not diesel, aliphatic material, that is indicative that is, if we are looking for contaminants, it is an indication of the petroleum hydrocarbon. And this is in light clay, so you can see that addition of this diesel will increase this peak in around the 2900. And if you remember again, so this mineral, this will be a kaolinitic dominant clay minerals, and this will be more of a elite or smectite dominant clay minerals. And in this paper, we're looking at how to predict total petroleum hydrocarbon in the soil. So if we look at this, the same region, that aliphatic region, that addition of diesel or petroleum hydrocarbon will increase dramatically the aliphatic contents of the soil, which normally is not that high. So if we isolate this region and we calculate the area with different increasing amount of petroleum hydrocarbon, we can make some kind of simple regression that this is related, the area of the region in this region is related to the petroleum hydrocarbon. And if we look at that if we just do a multilinear regressions relating the different regions of the infrared, the mid-infrared spectroscopy region. So this is only using 5 parameters. We get a calibration of R square of 0.75. But if we use the whole region from 4,000 to 700 wave numbers, 650 wave numbers, and using PLS, we got the R-square much higher of 0.89, but it uses the whole region's what we call 180 parameters to predict the same values. So although the R-square value is not as high as the PLS, but in this case, if we want to do a prediction whether the soil is contaminated or not, this is a quick way and a more reliable or more intuitive way of finding out if the soil is contaminated or not. And now the next question is, so we talk about this region, so what is the dominant clay mineral in this soil? And the answer, this is not a mineral soil because there's no indication of the peak of the mineral, but there's a high amount of aliphatic amount in this region. So this is a pit, this is a histosols, and there's no, about 55% of organic matter. So now we talk about the calibration method. Since the Beer-Lambert law is not observed, this is a near-infrared spectrum for different carbon content. Although some regions show some increase, but it's not perfect because of different soil materials, because soil is not a pure materials like because it contains different types of mineral materials and also different kinds of organic materials. So you can't really assign a particular peak or a particular region to as a different content because it's a mixture of all different sorts of minerals. So the shape of the spectra, the whole spectra itself, is more meaningful than the reflectance at particular wavelengths. So we need to have a multivariate calibration that use the whole spectra in order to predict soil properties. So usually the mathematical formulation, if it's a linear model, is what's our response. So it can be one variable, for example, soil carbon, and the predictors is the spectra itself, the mid-infrared spectra. And we want to find the regression coefficients, right? So it sounds simple, but the problem is that this is the Y value. It's only one value. It's only, for example, soil carbon, or we can say a couple of values. But the predictors, it contains n rows, say 100 soil observation, but P predictors, that P is ultra spectral, so it can be 1,000, it can be 2,000. So if you solve this in the mathematical, just normal mathematical way, you will get a non-definite answer. You won't get a good answers. And because the spectra are highly correlated, one reflectance value and the next one to it is highly correlated. So this is a large number problem. So there are more variables, more predictor variables than the number of samples, what they call as large P but small n. And we have to find a way to deal with it. So some solution is that we reduce the dimension of the spectra. So for example, calculating the principal components. Or the other way is variable selection. So we don't use the whole spectra, but we pick several spectra regions and do a calibration. There are different ways to do that, the linear methods, for example, PLS, or there are also machine learning methods. So PCA is the most famous method because it's established in statistics. It's been there for quite a long time. Is that we try to find a low dimensional combination of the high dimensional data. So if we have a spectra of a few thousand variables, if we can find we take those spectra and find a linear combination and then produce variables that are uncorrelated, then we can reduce significantly the number of variables. So, and the components are ordered that the first principal components has larger variance than the second and so on. So we won't go through in detail with this. But this is basically the simple mathematical model of a principal component. You've got a spectra, and you need to transform it into scores or the new descriptors using the latent structure or loading matrix. So, and we use this simpler scores to do the description, to do the mathematical analysis. And similarly, partial least square is based on the idea of a principal component. So rather than decomposing just the X or the spectra, it also looks at the Y or the response variables, and it produces a set of common orthogonal factors. So this is just a simple representation. This is the principal component. You get the spectra. You want to transform it into scores that are smaller number of variables with a loading matrix. But then on the other hand, simultaneously, you have the response as well, the Y variables. And it's also described as a score matrix. So there's a relationship between the score matrix in the spectra and the one in the response. And this is because it's related then the new descriptors have try to compensate both reducing the spectra and also trying to address the response variables. So now we go to the details of spectral data analysis, and just give you what we usually do in Sydney. So it's not going to be the perfect method, but it's what we found to be working. And of course, you can. Of course, this is not the definite method, but this is what we found to be the most. In most cases, works quite well. So we'll talk about measurement and spectral pretreatment and then modeling. So we usually take three triplicates and then we average it. So this is in the near infrared region, right? So it is similar to in the mid infrared regions, and then we convert the reflectance to absorbance, and then we filter it to remove the noise using Savitsky-Goulet filter. So it's just trying to smooth out all the noise. And then we trim it to remove the regions which have a high signal to noise ratios. And then we do a baseline correction. This is a thing called SNV. So basically you standardize it by the mean and the standard deviation so that the spectra have a mean of 0 and a variance of 1. So why do we do that? In many cases, because of different scanning conditions, you might have a slight higher reflectance, or if you scan it on one day or the other, there might be slight differences so this is trying to correct for that. And in mid-infrared, what people found also that the first derivative works as well, as quite good as well. So this is in the near-infrared, and in mid-infrared, people do a first derivative. And then we split the data into calibration and validation. So we use 75% as a calibration and 25% as a validation. So why do we need to do that? We need to know that in the model that we build, so if we just use the whole data as a calibration, because it is a multivariate analysis, because it got thousands of spectra, it's quite easy to get overfit. That means that it looks quite well in the calibration, but it's not necessarily have a predictive capability on the other spectra that the model has not seen. So in this way, we can assure, or at least we know something about what if we train the data on the 75% of what if we train the model on 75% of the data, and then we test it on the other 25% where the model hasn't seen the data. In this way, we can ensure that it performs as well as the calibrations. And then we use the Bootstrap aggregating. I'll explain it later. And then we use the Cubist model, which I'll explain it later as well. So spectral pretreatment. So there are different spectral pretreatment that are available in different software. Some people believe one spectral pretreatment is better than the other. Some people use one spectral pretreatment because it was found in the literature. But does it matter which spectral pretreatment do you use? So it can be first derivative, or the SNV, you standardize it, or some people use what is called the MSC, multiple spectral corrections, trying to remove the background noise. And some people use the continuum remove that try to enhance the peak of the spectra. Does it really matter? So it depends, and different people, there are different research, there are different papers that have tried all these different spectral pretreatment and try to see which one's better. So this is an example in the group of Sabine Grunwald, and also so they're trying to model soil carbon fractions with visible near-infrared and mid-infrared spectra. So don't worry about all the other columns. So this is, just look at this highlighted column. So this is the R square of a total carbon using different pre-processing methodology, pre-processing techniques. So if we look at it, there's not really much difference except for this one, the MSC. If you compare the raw or the MSC or the SNV or the first derivative, there's not really a lot of difference, although they say that the absorbance is the best one, but there's really not a lot of difference if you look at it, right? Except of this MSC with the first derivative, there's not a lot of difference in terms of the performance. And another study, this is from Andrew Silla in Kenya. So he looked at different pretreatment, and this is the R square value for pH and aluminum, carbon, clay, and sand, and this is the average. This is the average R square, first derivative, second derivative, MSC, SNV, and so on. So he found that the first derivative is the most useful, but MSC again is somehow give the lowest R square. But if you look at it, 0.8 and 0.79, 0.76 and 0.78, the difference is minimal. It's not that much of a difference. And this is the paper that says that it recommended that the selection of best pretreatment for an analyte be based on the combination of statistical testing and modelers judgment, which is very useful, or not really. So spectral pretreatment could be useful, but it's not going to enhance significantly the performance of your model. So if there is a relationship, there is a good relationship, it will show up as good relationship. You can't pre-treat it, and it won't, and to make it significantly improve. So minimal of spectral pretreatment is usually, or don't spend too much time trying to test different pretreatment. It won't give you much more. It won't give you much more improvement. That's my advice. Could be wrong. So the next thing after you treat the spectra, so either you do the first derivative or the SMB, then you do make a model. So in this, as we discussed before, we prefer to use a model which we call Cubist. Cubist is like a regression tree, but rather than forming a value as the end of the node or the leaf, so it gives a linear regression. So for example, in these cases, that it gives different rules. The rule number one is if the absorbance in the 2900, which in this region is greater than some values, and the absorbance in the 1900 greater than some values, then the total carbon is a simple, not a simple, it's a multiple linear regression. So it is a machine learning techniques which is used to find relationship with a lot of variables, and it the algorithm managed to pick up different important wavelengths that it used for prediction. So we did this in 2008 when Cubist was only available as a software, as a commercial software, but nowadays it is available as a open source or free add-in in the R software. So we did a comparison between PLS and Cubist, and there is a slight improvement. There is not a lot of improvement. There is an improvement in terms of the root mean square error. So it's 0.39 with the PLS, and the Cubist is 0.35. But if you look at the value of low carbon concentration below 1, below 0.6, we can see that this is the prediction of PLS, which is quite not that good because it has lots of scatters and sometimes it predicts negative values, right? And the root mean square error is just 0.25. But if we look at this region in the Cubist model, although it's not great, but there's no negative value, and it predicts closer to the 1-to-1 line, and the root mean square error is much lower. So overall, because of the dominance of the high carbon values, you may not see the improvement, but on the low carbon content soils, like in Australia, you can see that the Cubist model actually gives a better prediction. So we like this because it is more accurate, and because of the variable selection, it doesn't use the whole spectra. It only uses a certain number of wavelengths. So for example, in this example, the Cubist only uses 42 wavelengths, while the PLS use the whole wavelength. And you don't have, because you can control the number of extrapolation, you don't need to have a negative carbon content. And in this example, we don't do any transformation. We just want to see what's the performance of the model. And so how about the Lincoln data? So we did a simple experiment. This is using your data, the KSSL data. So we selected 11,000 data points on the mid-infrared spectrum. So we haven't done any pre-treatment, just a simple smoothing and absorbance. We don't tune anything. So this is with the PLS. This is the calibration, the same with the PLS with the Cubist. So in this case, we do log transformations, but this is in terms of carbon content, we transform it back. So we can see that the Cubist model, so this is 11,000 points, 11,161 spectra from your own spectra. So we can see that in the calibration itself, it performs much better. And in the validation, 3,700 that we set aside, which is not used in the model, we can see the prediction is quite good as well compared with the PLS, which you see much more scatter. And this is the default setting. There's no optimization yet. We haven't do much of optimization, but it's just showing, just a quick way of showing that it does show a better performance in large data sets. And this is again the total carbon comparing Cubist and the PLS. We can see in most properties that the validation. This is on the validation. It shows improvement over the PLS. But we can further improve it with different types of models. So one way of, if in case you have a large data sets like the KSSL data set, then we can do lots of what they call as a data or model ensemble. We create lots of model and then put it all together. One simple way is using a thing called Bootstrap and Bootstrap aggregating, or what they call as bagged models. So if we have the original data sets, let's say you have 10 data points, and then we do a Bootstrap sampling. What does the Bootstrap sampling means? That is sampling with replacement. That means that we sample the data, 10 values, but each time, but when we sample it, we can, what they call a sample with replacement. So if we imagine that there's a jar of 10 values, we take one values and then we note it down, and then we put that sample back in the jar again, and then take another one in random. That means that there are some points, like the 8th point, that can be sampled twice, but also means that there are points where it won't be samples. So we do this many times. At each Bootstrap, we make a tree model, or we make a PLS model or other models. And then at the end of we can do 50 Bootstrap or 100 Bootstrap. At the end, we average the output of each of these models. So why do we do that? Because at each Bootstrap, if you look at it, it samples a part of the data or 2/3 of the data, and then it fits the models. And the second Bootstrap, it also samples 2/3 of the data, and then it has the test data, which is not sampled. That means that you make a model at different parts of the data that are different configurations of the data. So at one point that maybe the model is stronger in one part of the data, but maybe not on the other parts of the data. And if you aggregate it later, you get a more enhanced prediction. And in addition, that because you at each time you set aside automatically some test data that is not seen in the model, you can get accuracy of the model itself. So this is what we call this Bootstrap aggregated models, that you sample the data, you make different realizations of the data, and you make different models from the same data set. And how do we assess prediction quality? So there are different ways of assessing prediction quality of how good your model is. And usually it's recommended that you assess the quality of your model on the validation data set or the data set that you set aside for testing. And the most simple one is called the root mean square error, which is a measure of accuracy. Some people also call it the standard error of prediction. So it's simple. First, we calculated the mean square error as the name itself. This is the observed, and then this is the predicted, and then you square it, and then you take the mean of it. Sorry, there should be 1/n here, and you take the mean of it. And the root mean square error is just the root of the mean square error. Because mean square error gives you the square values, but if you take the root, then it gives you back to the same unit that you are measuring. So it's also called standard error of prediction. And the second one is the mean error, which is just a simple of sorry, there should be a 1/n of is the average of how much is predicted over the take away what is observed, which is called a bias. So why do we need to do that? So imagine that you have a measured values and the predicted values. So the predicted is somehow, this is the 1-to-1 line here. That means that ideally you want it to all the prediction and the measured value should be all in 1-to-1 lines. But sometimes the model has a bias. That means that sometimes the model can overpredict, systematically overpredict. So this is what we call as bias. That means that we need to know that whether the model is biased or not. And the root mean square error is a measure of the spread of the error of the data. So if we take that the normal distribution, 95% of the errors is in the bias minus 2 times standard error of prediction, and the bias plus 2 times of standard error of the prediction. So sorry, this should be SEP. So this is 4 times. So this is give you a rough approximation of how much the root mean square error gives you the idea of how much error or the spread of the error of the model. And the bias gives you the idea of how much of it departs from the 1-to-1 line. And also some people like to use R-square value, which is 1 minus sum of square of the error or residual over the sum of square of total. So in linear model, this usually tells you that how many % of the model has explained the variance in the data. But the problem is that, for example, in this case, if the measured and predicted is on the 1-to-1 line, the bias is near 0 and the R-square is 0.83. But if the prediction is biased, if it shifts the same data, but it shifted 0.6 of a unit up or over predicted, the R-square values will not change because it tells you about the linear relationships. The R-square is 0.832, the same R-square, but the bias, there is a bias. So it is important to include bias and the root mean square error in when you're reporting the statistics. And some people like to also use what is called a Lin's concordant correlation coefficients to counter the effect of that the R-square values doesn't change if it's not on the one-to-one line. So this concordance correlation coefficient evaluates the agreement, but it has to be the agreement if the measuring the variation from the 45 degrees line. So just for example, we have two methods here for measuring soil resistance. So this one is unbiased. So the concordance correlation coefficient is 0.7. This one is actually the same prediction, but it's biased by, so this one, the bias is 0.6, and this one's the bias is 0.9, so there's about 0.3 difference over predictions. And you can see that the concordance correlation coefficient decrease the same value, but the R-square value will be the same. So the concordance correlation is, it took account that it has to fall in the one-to-one line. But there's also other, especially in the spectroscopy world, in the spectroscopy literature, that says that you need to use RPD to measure how good your model is. So RPD is called the ratio of performance to deviation. So it's a standard deviation of the data divided by standard error of prediction, or the root mean square error. And some people give different categories that say it's an excellent model if your RPD is greater than 2. It's a fair model if your RPD is between 1.4 and 2, and it's not a reliable model if RPD is 1.4. I don't know how they come up with the number, but it seems like it's a default value, and people tend to use it to justify that the model is whether excellent or fair or non-reliable. But in fact, RPD is assumes that it only works well in a normally distributed data because it relies on the standard deviation. And as I'll show in some example, it's not really a good measure. And the second one is RPD is exactly the same value, the same as R square. So if remember, R square is 1 minus sum of square residual over sum of square total. So R square is in terms of variables. This is a mean square error. This is the variance, and this is the standard deviation. This is the root mean square error. So in fact, they relate one to the other. So an R square value has a relationship with the RPD value. So the other worrying thing is that, for example, RPD difference between 0.8 and 0.9, R square value 0.8 to 0.9, will result in a high increase of the RPD value. So R square of 0.8 is about the RPD of 1.7 or something, but 0.9, a slight difference in the R square will translate into a high increase of RPD, which is artificial, it's not real. So I'll give you an example. So this is, for example, a prediction of total carbon, which is quite bad. So this is the one-to-one line, and the R square value is 0.34. The standard deviation of data is 0.72. The root mean square error is 0.74. The RPD is 0.97. It's less than 1.4. You say it's a bad model. And even the concordance correlation coefficient is 0.41. Right, the same data is 23 data points. So, but on the same data set, I add 2 data points, which is quite high. This is the same data set, the 23 data points as before. I only had 2 data points, but you see now my R square is 0.97. And because of the standard deviation is increased significantly relative to the root mean square errors, now I got the RPD of 2.8 greater than 2. Which is excellent models, and even I can get the concordance correlation coefficient of 0.9, which is say is excellent, but it's the same model as this. It's a bad relationship, but you can make it real good if you have 2 outliers, if you have some outliers. This is not saying that it's not useful, but it's saying that you have to be careful, and if you want to get I'll give you a tip if you want to get a high R square. Put a couple of high values leverage, and then it will give you a high R square. So this is all relative. You have to look at the data, and you have to understand that this is a statistical measure, and it has flaw on it, and it's not going to improve your model. It's not going to be a definite that R square value of 0.8 should be excellent, or RPD value of greater than 2 should be excellent. It's all relative. Then you need to be careful and when interpreting the model and data. And the next I'll talk about which soil properties that I can predict with the MIR. So the MIR usually can predict, because it's related to the minerals and the components, it should be able to predict minerals and the components and the organic matter, and then surface physical and chemical properties. So this is example that this is predicting the carbon fraction. So the carbon fractions, so we can predict total organic carbon, or the humidified carbon, carbon that has been humidified, particulate organic carbon that is from particulate matter, and the resistant organic carbon. So this is on the Cubist modeling on the calibration data that was given to us from the CSIRO. This is 200 points. And they also withheld the validation data sets of 87. So this is on the validation as well. So we can see that it replicates the data quite well. And this is using Cubist with untransformed data. And we compare with the PLS modeling that's done by Jeff Boulder in South Australia. We got a similar or sometimes even better prediction. But we can do also different fractions of carbon, and this paper, if we try to predict the different forms of carbons in the macro aggregate, or organic mineral carbon, because this is, to do that in the lab is quite a laborious procedure, because you need to take the soil, the aggregates, you need to disperse the aggregates and then sieve it and so on. So mid-infrared is because of its ability to detect carbon, because it's a fundamental bond. It can detect the carbon fractions quite good. And of course, total carbon, but it also depends on which measure of total carbon. Usually, if it's measured by dry combustion, the standard method, like this on the right, you can get a very good prediction. But if it's Walkley and Black, because it's not a complete, because it's dependent on the oxidation method, usually it's not as good as the Blaco or the dry combustion method. It can predict total nitrogen because it's related to organic matter, but of course it cannot predict something that is labeled, for example, nitrate or ammonium, because it's dependent on the extractant. And particle size analysis, clay, silt, sand is, clay and sand particularly is quite good. Silt, it depends, sometimes it's not as good. And CEC, because it's related to the mineral and the surface area of the minerals, and also to do with the organic matter, is predicted quite well. And even CEC over clay, which can be indicative of the mineral types, or clay mineral types, can be predicted reasonably well. But it also can predict a total element, for example, total potassium, total phosphorus, total sulfur. I'm talking about total values, not available values. And in some cases, this is a rare cases, it even can predict related to the surface chemistry, for example, electrical conductivity, which is related to the salt concentration, but maybe in this case it's because there are some highly saline soils, the high values that it can, although it's not predicting that well, it can separate out saline from non-saline soils. ESP is lots of scatter, but it's, as an indicator, it can probably separate out soils that are highly sodic and non-sodic, and also chloride. And this is just an example that we did in some data in 2009, and we can see that it all, like for example, CEC, clay, sand, organic carbon, total, it predicts quite well. Exchangeable calcium and magnesium, because it is the most dominant elements in the exchange capacity, but not that much of the potassium, and pH reasonably well, total reasonably well, but then when you come to extractable like DTP, extractable copper and so on, it's not that well predicted. And also related to, for example, available phosphorus and acid extractable phosphorus. It's not well predicted, but phosphorus absorptions is well predicted. So things that are related to the surface area, to the surface chemistry of the soil is well predicted, but the one that's related to the chemistry, to the solution chemistry, extraction chemistry, is not well predicted, which all makes sense. But then there are some papers that claim that mid-infrared can predict soil hydraulic properties, which is quite controversial. Well, I'll say controversial because soil hydraulic properties, field capacity, wilting point, hydraulic conductivity, it depends on the pore size distribution, the shape of the pores and how much pores and how connected the pores, and also to do with the transport of water, solute and gas. Can it really predict? Well, I'll say no, but some papers say yes, but I'll take through you. We'll go through some example and you'll see whether it makes sense of or not. So let's take an example. A soil. This is one soil. This is from the literature. The dashed line is the water retention of the soil without compaction, and the solid line, the black line, is the soil after compaction, right? So this is one soil. Take, for example, this soil. This is not compacted, and this is compacted. The bulk density on the non-compacted is 0.97. After it's compacted, is 1.3. Decreased porosity, decreased field capacity, decreased wilting point, and decreased hydraulic conductivity because the pore space has been decreased, right? And then you take these two soils and you bring it to the lab. You sieve it, and then you put it in the plate, and then you scan it with the NIR, or for the MIR, you further ground it to 100 microns, and you put it in the plate, and then you put it in this Tensor or the Brooker MIR instrument. So tell me the logic that these two soils that are different because of the structure, after you sieve it and then tap it down and measure it, can tell you the difference of hydraulic properties. This one has a higher field capacity, then this one has a lower field capacity. There's no logic at all that you're measuring these soils that has been ground and further powdered, and then you're going to tell me that it's going to measure the field capacity or hydraulic properties. On saying that, you can say that maybe it's to do with the pore size distribution. So there are a few studies that compare. This one is from the Christine Morgan from Texas A&M, between the air-dried soil and the intact soil. So this curve here, air-dried soil, and this one intact core soils, the reflectance. That's not really, the shape of it does not really change much after you ground it. So there's no indication in the spectra itself, in the peak itself, that is going to tell you that this hydraulic properties is going to be different from these hydraulic properties. Having said that, the reflectance may be affected. So this is on your this right-hand side. This is a study, quite a good study by Jose Damate from Brazil. So he looked at he took a soil core and then he scanned it, and then he compressed the soil, and then it's compact the soil, and then scan it again. So what he found is that because of the compaction, if it's non-compacted, because of the illumination of the infrared, it can get more into the soil. But if it's compacted, the pores are smaller. That means that there are fewer pores and there are more reflections. But this is in terms of reflections, that in the non-compacted soil, there is less intense of the reflectance, and if the soil is compacted, there are higher reflectance, but the shape, overall shape is similar. That means that this soil reflects more of the infrared spectrum. But this is in terms of a very careful experiment trying to see what's the effect. So this is in terms of a core, but for real application, I can't see how it can detect porosity. And we can see that although there are some papers that claim to this and that shows a good relationship, but it's all to do with the data. For example, in this article, it shows that it can predict well water content at 10 kilopascal, which is for Australia equivalent of field capacity. But these soils, if you look at it, the water content goes up to 60 and 80% water content. These soils are ground soils, which are not impact soils when they measure the volumetric water content. We have access to those soils as well. This is ground samples. This is 10 kilopascal. The R square is quite high. It's quite good because it's ground samples, so it's measuring things related to the surface area of the soil, and the 1500 kilopascal, or the wilting point, also is quite good because 1500 kilopascal is more related to the adhesion of water and the surface area of the water, and that's why we call it, this is the gravimetric content on the ground samples. If we look at ground impact core samples at the low potential at 1500 kilopascal, we got a reasonable prediction. But at 10 kilopascal and 1 kilopascal, the blue and the dot here, we can't really see any good relationship because it's impact core samples. It's related to pore distribution. You won't expect to see anything to do with the field capacity with infrared over there. And then also, of course, hydraulic conductivity, there's no relationship with the mid-infrared spectra, and also bulk density. There is no reason why mid-infrared, after you ground the soil, you can see the bulk density. And there's a paper that's out there that says that near-infrared can predict soil bulk density. If you look at the plot here, do you really want to predict bulk density with near-infrared spectroscopy? If you look at the range of the data is between 1 and 2, but the prediction is only really is around 1.3 and 1.5. So you can probably do a better guess with your eyes rather than use an infrared spectrum. But having said that, other properties that are related to the surface area, the engineering properties like liquid limit, plastic limits, it can be probably predicted quite well. So this is the surface composition that the clay particle size carbon CEC that can be predicted well. Soil solution chemistry that are probably not predicted well. And then pore space, which cannot be predicted, which relies on bulk density. But there are solid composition like string soil properties, plastic limits that can be predicted. So what we are suggesting that rather than predicting water retention directly, you can use a spectral inference system. What does it mean? For example, the spectra itself, then you can predict with the PLS, the particle size and organic carbon. And when with the information of the bulk density and the particle size and the organic carbon, you can use a pedotransfer functions, which has already been established a lot in the literature to predict your moisture retention. In this paper, we're trying to compare this. So this is if you predict 10 kilopascal, 100 kilopascal, and 1500 kilopascal directly from the mid-infrared. I mean, you can't really predict well the 10 and 100 kilopascal, which is more related to the structure of the soil. But in the pedotransfer, because it uses information about the bulk density, you can predict not that well, but reasonably well spread value of field capacity and 10, 100 kilopascal. If we use the information, basic information from the mid-infrared, the particle size, the organic matter, and add information about the bulk density, which can be predicted, we can probably reasonably predict better than just predict it from the mid-infrared spectrum. And of course, the mid-infrared spectrum, because it's it is related to the minerals. It can predict geochemical concentration. This is a recent example from France where we predicted total silica in France from mid-infrared. We can see a very good prediction of total silica. And then there are various literature that you can quantify the elemental concentration, aluminum, magnesium, calcium, total iron, and then you can calculate the weathering indices, which tells you about the weathering of the soil that you can compare. And there's also opportunities combining multiple sensors. For example, you can combine the VIS-NIR with the MIR or VIS-NIR with the MIR to give you better prediction. So there are different ways. One is called the model averaging. That means that you've got one spectra, for example, the VIS near infrared, and you get a model, and then you have a model prediction for the near infrared. And the other is the mid-infrared. You've got the spectra, and then you can get a mid-infrared prediction. And the model ensemble is just you combine what's the prediction based on near-infrared and what's the prediction of based on mid-infrared. That's called model averaging. And the other one is spectral ensemble. That means that you got a visible near-infrared spectra, mid-infrared spectrum, and then you combine the whole spectra and do a spectral modeling. So either just by a concatenation, you got the different regions of the infrared, and then you combine it and you do it for modeling, or you do something called the auto product analysis. That means that one signal from near infrared and the other you multiply it and become a matrix, which in some cases may be able to enhance the prediction. This is an example where with the data from the geochemistry in Ireland by Sharon O'Rourke, who came to visit our lab. So we tried to use whether the VIS, NIR, MIR, and XRF can be used to determine soil geochemistry. So this is geochemistry in, they have 40 elements in from the Irish National Soil Database Archive. And the thing is that these are from agricultural soil. That means that they are not contaminated soil. And one thing about XRF is although it can give a good prediction of the direct prediction of the elemental concentration, it has its limitation of the detection limit. So for example, the one in the grayish color is less than 1%, and the one on the blue color in different concentration, that some of this is related to the micronutrient. The detection limit is quite small, like a 5 ppm or 20 ppm. So in soil itself, it can be a problem if we want to detect, if it's non-contaminated soil, if it's agricultural soils, can we predict it? So this is surprisingly, like we look at 40 elements, so from pH, carbon to all different elements. If we look at it, the one that is on the validation with the most accurate spectral methods, sometimes mid-infrared shows up better than the XRF itself, because this is a non-contaminated soil, so the concentration of some of the elements are relatively low, and the mid-infrared sometimes is better pick it up than the XRF itself, and even some methods is better predicted by the near-infrared. So what we're suggesting, rather than relying on one method or the other, because there are information in the mid-infrared which is not available on the XRF and vice versa, that you can combine those mid-infrared and XRF, which is just a simple model that this is prediction from the mid-infrared, this is prediction from the XRF, and then we find the coefficients that can best predict the concentration. And if we do that, we can, if we do that on this table, we can see that the prediction improve on some of or most of the properties. The study says that compared with any single spectral method, the number of soil properties or elements that can be predicted well increase from 15 to 25 when you combine the XRF and the mid-infrared. And then we got 25 soil properties that can be well predicted from pH, carbon, and different major nutrients, some major elements, some trace elements, and some trace elements of special interest. But of course, there are some elements which remain difficult to detect in the soil. I'll probably skip a little bit about this. I'll go to about the final one about the spectral inference systems, which I talk about that. Probably it's better to combine, if not predict everything with the mid-infrared spectrum, but if we can combine it with the pedotransfer functions, which has been established quite well in the literature because the USDA has a large amount of data that has been well established, then we can build relationship that we can predict with the one with difficult to obtain using a network of pedotransfer functions. So what does it mean? So for example, we scan some soil and then we predict some basic properties like a clay, but then using that information, we can predict further information from other properties. I'll show you an example. For example, first is that we predict, the one that we know that we can predict quite well is total carbon, pH, CEC, clay, sand, EC, and this is given where the position in the soil profile. But using this information, we can propagate to see how, because there are relationships, for example, shrinkage, organic matter, and the pH in calcium chloride, and the pH buffering capacity, bulk density, which are depending on all these properties. So if we can propagate what we measured with what can be established from the network of pedotransfer function, we can get a good prediction. So for example, in this field, this is scanning the soil with a VIS-NIR. We can get directly prediction of organic carbon and clay content. So the first line is what we can establish, what we can confidently establish. And the second line, what is we can infer from that. This is water content at saturation. This is bulk density, this buffering capacity. So each one of this is different layers of what further information we can infer from this first line. So water content at fill capacity, different parameters of the Van Newton equation, and the saturated conductivity. And at the end, we can do some kind of inference. So for example, these soils that we can calculate how much available water, not just from the spectra, but just from the spectra plus some information about the soil, about the structure. And then we can do some recommendation. For example, this soil, because it's a sandy soil, it gets high sand on the top 50 centimeter, but it's got heavy clay that is non-expensive, non-infertile, no calcium carbonate. You can't do this. It's not going to give you a good cropping system. This side, it has a moderate available water capacity. It's quite fertile. You've got a thick. And this side is a vertisol. It's clay, fertile, high available water content capacity. You've got a big thick. And in summary, so that mid-infrared combined with chemometrics and machine learning provide a powerful techniques for prediction of soil properties. There are properties that can be predicted quite well, which is related to minerals and its components, physical properties related to the surface area of the soil, organic matters, and chemical reactions related to surface. But also we need to be critical, evaluate if the prediction makes any sense. We don't predict field capacity. It may give you good prediction, but try to evaluate what makes it, why does it do that. And if we have a spectral inference systems, maybe it's better to combine the small spectral prediction with existing soil knowledge that we already know from the building of pedotransfer function or rule of thumbs and so on. And sorry, it takes a while, and thank you guys for your attention, and for those people in the South, thank you all.
All right, well, thank you, Buddhaman, and I'm going to remind people that if you have a question, to put that in the Q&A, and we'll take those questions as they come in. Any questions from people in the room with me?
Hey, Budiman, I'll ask the first question, I guess. This is Rich. What are your thoughts on using, I'm not as familiar with Cubist. I'm starting to learn about it, but what are your thoughts on using locally weighted regression analysis to handle large data sets as contrasted with other approaches that have been considered?
Sorry, yeah. I think if you have a large data set, it makes sense. It makes sense if, for example, if you have a local, if you are doing a local area, trying to use data that are more related geographically or soil related, rather than using the whole database, which is more going to give you more local information. I think that it does make sense. Although some literature, some studies show that there's no benefit, but I do think that it's still, when you have such large data set, if you make models on large data set, it's tend to be more general if you have trying to predict on a smaller areas.
Yeah, I'm just wondering how that approach would compare with Cubist or some of these other neural networks or all these other approaches that I've been reading about.
I think neural networks or Cubist or other things, it's just a tool, it's just a regression tool. So I think you can still find local data or local relationships and train the local data using any tools you want, PLS or other things. Yeah.
Yeah, I'll be eager to see when someone comes up with this is the official best way to handle, data processing for this property, and this is the way to best handle the data set for this property, because it seems that not one size doesn't fit all in terms of how to model different properties.
So we have a question from Shri. I have a question regarding prediction uncertainty. How to estimate uncertainty for each individual prediction. Root mean square error generally shows the overall model performance, but ignores how precise each prediction are.
Yeah, good question. So, yes, so for the individual prediction, you can do what they call the Bootstrap prediction, but then again, that's to do with the prediction, the model uncertainty. So if you generate lots of model, if you generate 50 models on the same data set, that means that at each prediction you can calculate how much of those 50 models vary. So if it varies a lot, that means that the model is not that stable, and more likely that the prediction is highly uncertain. But if the model is give you a small uncertainty, if every time they give you similar prediction, you can be certain that the model can capture the variation in the data. But that's to do with the model uncertainty.
This would like to get your take on perhaps the future of spectroscopy. The KSFL, we do a fairly extensive prep of grinding and drying the sample. Mm-hmm. At what point do you think the spectroscopy will be used in the field to do what we're doing now without, sample prep and so on?
I think, I can talk about the current one. I think the current one is, the mid-infrared gives you excellent properties, but I think it's affected a lot by the reflectance can be affected by the surface area and also the moisture, so that it's not that suitable for the field application. Although they are portable, so-called field mid-infrared spectrometers, but the data it gets out of it is quite noisy because of it's not smooth. But in the field, I think we have to still rely on the near-infrared spectroscopy. So although it cannot give as good indication as the mid-infrared, I think but it's quite robust because it's not affected so much on the surface area of the condition of the soil, and there are ways of handling to do with the moisture that you can remove the effect of moisture. So in near-infrared spectroscopy probably give you a good indication to start with, but if you can say that it's your toolkit that you bring in the field, but if you want more reliable data, you can take it in the lab and doing the mid-infrared. And there are also, I think, coming up recently, probably in 5-10 years, you will be getting more and more the portable miniaturized near-infrared spectrometers that will be as good as the more expensive, like the standard desktop or benchtop near-infrared spectrometer.
All right, well, that sparked a few more questions to come in. So Finney asks, would it make sense to combine different IR sensors, but also e.g. ISE electrodes in the field?
Yeah, sure. I think, probably because, as we say before, that the near-infrared cannot really detect the surface, the solution chemistry of the soil. But probably the ISE, that if you do some solution, the extraction, probably it is going to give more information. So I'm not saying to combine the IR sensors, but each sensors, I think it gives different all good information, but different information. But maybe with the output from the ISE and output from the IR sensors, it can give something else. It can infer something else. That's what we are talking about, the inference system. So not just relying everything on the infrared, or not trying to relate everything on the other sensor. But if we can combine all different predictions, I think it will be a powerful tool.
And Libby asks, you mentioned a correlation of spectrum with depth. Is there a paper which describes this?
Not sure what you mean by correlation with depth. I mean, they are the near-infrared. This comes up more from the near-infrared field research that people try to characterize the spectral of the near-infrared with depth. I mean, there are several papers which I can share later.
Okay. And I think that has exhausted all the questions.
I'm exhausted as well.
So thank you, Budiman, and thanks to all the participants for joining in. We hope you found this information beneficial. We had about 70 people join today's webinar. We'll pick up even more as the recording is posted on our National Soil Survey Center YouTube channel within a couple of days. So feel free to let your colleagues know about this training opportunity. And this concludes our webinar presentation.